June 4, 1996. Europe's most powerful rocket lifts off for the first time, and 37 seconds later, it self-destructs in the sky. No engine failure. No explosion inside the rocket. No structural collapse. The cause? A software error, a single data conversion that should never have been possible. Tonight, we break down how one line of code destroyed a $370 million mission, and changed space engineering forever. If you want real space stories. Without hype, without myths, without fictional drama. Subscribe to Astrocatastros. Because space doesn't reward what we believe is safe, it rewards what we prove is safe. The Ariane program had already made Europe a serious space power. Ariane 4 was reliable, predictable, profitable. But the future demanded something bigger, a rocket capable of launching heavier commercial satellites and competing with the United States and Russia. That rocket was Ariane 5. It wasn't an upgrade. It was an entirely new launch system, new engines, new flight profile, new guidance software, new onboard computers. Everything about Ariane 5 was designed to push performance forward. But pushing performance also pushes risk, because every new system introduces something engineers fear more than hardware failure: unknown behavior. Why software became the critical system? Earlier rockets depended heavily on mechanical and analog systems. By the 1990s, rockets had become flying computers. Guidance, navigation, stabilization, engine timing, everything depended on software running perfectly in real time. Inside Ariane 5 were inertial reference systems, or IRS units. These systems continuously calculated the rocket's position, velocity, and orientation. Without them, the rocket would not know where it was or how to correct its path. To increase reliability, Ariane 5 carried two identical IRS computers, one active, one backup. If the primary failed, the backup would instantly take control. It looked like perfect redundancy. But both systems shared something dangerous: the exact same software. A small piece of reused code. When Ariane 5 was being developed, engineers reused parts of the Ariane 4 software. This decision made sense. The older software had already flown successfully many times. It was considered safe, stable, and proven. But Ariane 5 had a very different flight profile. It accelerated faster, reached different velocity ranges, experienced different horizontal motion patterns during ascent. And inside the reused software was a function designed to convert a 64-bit floating point number into a 16-bit signed integer. Under Ariane 4 conditions, the value would never exceed the safe limit. Under Ariane 5 conditions, that assumption was no longer true. And the system was about to learn that lesson in the most expensive way possible. The first 36 seconds. Launch day looked perfect. Weather conditions were clear. Systems reported normal status. Telemetry streams showed stable performance. At ignition, Ariane 5 rose smoothly from the launch pad, its twin solid boosters delivering enormous thrust. During the first seconds of flight, everything worked exactly as designed. Guidance systems calculated orientation. Flight computers adjusted the trajectory. Engine systems maintained proper thrust levels. To mission controllers, the rocket looked flawless. But deep inside one of the onboard computers, a number was quietly growing, a velocity value that the reused software had never been designed to handle. And that number was approaching a critical limit. Inside the inertial reference system, software continuously performed calculations converting floating point velocity data into integer values used by other systems. This conversion was safe, as long as the value stayed within a predefined range. But Ariane 5 accelerated differently from Ariane 4. The horizontal velocity component increased faster than expected by the reused software. At 36.7 seconds after launch, the value exceeded the allowable range for the conversion. The result was an overflow error. The software was programmed to shut down the system when such an error occurred, a safety feature intended to prevent corrupted navigation data from spreading through the rocket's control system. The primary IRS computer shut down. Instantly, the backup IRS computer took control, but it was running the same software, receiving the same data, and encountering the same overflow condition. Within milliseconds, the backup computer shut down as well. For the first time since liftoff, Ariane 5 was flying without valid guidance data. And the flight computer didn't know it yet. When both IRS units stopped functioning, they transmitted diagnostic data to the main flight computer. But the computer interpreted this diagnostic information as actual flight guidance data. The rocket suddenly believed it was veering sharply off course. In response, the control system issued extreme correction commands. Nozzle actuators moved aggressively. The rocket began tilting. Aerodynamic forces rapidly increased. Within seconds, Ariane 5 rotated far beyond safe flight angles. Structural loads climbed beyond design limits. At 37 seconds after launch, automatic safety systems triggered the self-destruct command to prevent debris from falling unpredictably over populated areas. The rocket exploded high above the launch site. A mission that had taken years to design and hundreds of millions of dollars to build ended in less than a minute. And investigators now faced a difficult question: how could a single software conversion bring down an entire launch vehicle? Within hours of the explosion, debris recovery teams began collecting fragments of Ariane 5 from the launch zone. Telemetry records were preserved. Software logs were analyzed. Engineering teams across Europe were mobilized. Investigators quickly confirmed something unusual: the engines had worked correctly. Fuel systems had performed normally. Structural components had shown no early defects. The rocket had not failed mechanically. It had failed digitally. Attention turned toward the guidance system, specifically the inertial reference system software reused from Ariane 4. What investigators discovered was not a hidden flaw, but a documented assumption. The software contained a conversion routine that engineers believed would never experience values exceeding a specific limit during flight. Because of that assumption, certain overflow protections were disabled to reduce computational workload. The decision made sense for Ariane 4's flight profile. But Ariane 5 was not Ariane 4. And the reused software had never been fully retested under Ariane 5's new trajectory conditions. The rocket did exactly what the code allowed, and the code failed exactly where engineers believed failure was impossible. Before, the assumption grew that it would work again. But aerospace engineering punishes assumptions that cross system boundaries. A program validated for one environment does not automatically remain safe in another. The investigation concluded that the failure came from a combination of software reuse without complete mission profile testing, disabled overflow protection routines, risk assessments based on previous rocket performance rather than new flight dynamics. In other words, the failure was not technical complexity. It was confidence carried forward without re-verification. Ariane 5 Flight 501 changed how aerospace organizations approached software certification. After the investigation, multiple reforms were introduced: mandatory mission-specific software validation, stronger simulation testing across full flight envelopes, requirements that reused software must be requalified for new operational conditions, improved fault handling systems to prevent shutdown cascades. The aerospace industry realized something critical: hardware failures are visible. Software failures are silent, until they control the vehicle. From that point forward, space agencies began treating software as mission-critical structural infrastructure, not just supporting electronics. And the lessons from Flight 501 quickly spread beyond Europe, influencing NASA, commercial launch providers, and defense aerospace programs worldwide. Ariane 5 Flight 501 did not fail because rockets are fragile. It failed because certainty is fragile. The vehicle was powerful. The engines were precise. The launch systems worked exactly as designed. But one assumption, carried forward from an earlier rocket, moved silently through the system, untouched, unquestioned, and unchallenged. And when reality finally tested that assumption, the rocket had no way to recover. This is why aerospace engineering treats every new mission as a new environment. Not because engineers distrust the past, but because physics does not honor experience. Flight 501 changed how the world writes flight software. It reshaped verification standards. It reminded engineers that reuse without revalidation is risk, even when the code has worked perfectly before. Today, every modern launch system, government or commercial, carries lessons that trace back to this single failure. Because in spaceflight, success is not built only on innovation. It is built on remembering the moments when confidence was wrong. And Ariane 5 Flight 501 remains one of the clearest reminders ever recorded: space does not punish ambition. Space punishes unchecked assumptions.